How does thermal shock damage ceramics? Imagine holding a glass of ice water and then pouring boiling water into it. The sudden temperature change can cause the glass to crack or shatter. This is similar to what happens to ceramics when they experience rapid temperature shifts. Ceramics are materials made from clay, silica, alumina, and other compounds that are hardened by heat. They are known for their strength and resistance to wear, but they are also very brittle. When subjected to quick temperature changes, they can suffer from thermal shock, which leads to damage. Thermal shock occurs because ceramics expand when heated and contract when cooled. The problem is that this expansion and contraction happen unevenly during rapid temperature changes. The surface of a ceramic heats or cools faster than the inside, creating a temperature difference called a thermal gradient. This gradient causes different parts of the ceramic to expand or contract at different rates, which puts stress inside the material. Since ceramics are brittle, they cannot stretch or bend to relieving these stresses. Instead, they develop tiny cracks that can grow larger over time. The process begins with heat transfer. When a ceramic is suddenly heated or cooled, the outer surface reaches a different temperature than the interior. This creates a thermal gradient, which leads to internal stresses. If these stresses are strong enough, microcracks form at weak points like pores, flaws, or sharp corners. These tiny cracks act as starting points for larger cracks to develop. As the cracks grow, they weaken the structure and can cause the ceramic to break apart. Several factors influence how much damage thermal shock can cause. One is thermal conductivity, which is how well the material can spread heat evenly. Higher thermal conductivity means heat moves faster, reducing the temperature difference inside. Another is the coefficient of thermal expansion, which measures how much a material expands when heated. Lower coefficients mean less expansion and less stress. The stiffness of the ceramic, measured by Young's modulus, also matters. Softer ceramics can absorb some stress better. Fracture toughness, or the ability to resist crack growth, is another key property. Microstructure plays a role too. Smaller grains and fewer pores help resist crack initiation. External constraints like mechanical restraints can increase internal stresses by preventing free expansion. In real-world applications, ceramics are often used in environments with rapid temperature changes. For example, engine components, kiln furniture, or thermal barrier coatings all face thermal shock risks. To prevent damage, engineers select materials with good thermal shock resistance. They also design components to avoid sharp edges and stress concentrators, which are spots where cracks are more likely to start. Sometimes, they modify the microstructure to improve toughness or use coatings to insulate the ceramic surface. Thermal shock resistance is often measured by how much temperature difference a ceramic can handle without cracking. Some ceramics can withstand temperature changes of several hundred degrees Celsius if conditions are right. However, if the temperature change exceeds the material's limit, cracks will form and cause failure. This is why understanding how thermal shock damages ceramics is so important for designing durable components. It all comes down to how quickly and unevenly heat moves through the material and how well the ceramic can resist the resulting stresses. Knowing these facts helps us choose the right ceramics for tough thermal environments and avoid unexpected failures.